John Harlim, who will be talking to us about learning solution operators.
Okay, so for this talk, right, I mean, I will go around the world to basically find tools to sort of capitalize these basic tenets assumptions that high-dimensional data typically rely on low-dimensional manifolds, whatever that means. So basically, one takeaway is like, maybe there's a better basis functions or dictionary you should represent your solutions. That's basically the point that I want you to get out from this, and hopefully with that, we don't need to do heavy duty journalism. So that's sort of what I want to go in this direction. So to do that, let me, I don't know among the audience whether anybody encountered the words diffusion maps. It's just one of this method that was being introduced by cognate and Lafont. They for unsupervised learning, and the way they do it is they sell it as a dimensional reduction tools. But let me go and talk about it. Okay. So what is this diffusion maps? Basically, I can summarize it. It's just basically based on this following asymptotic expansion. Suppose I have a kernel k epsilon, so in here, let's say exponentially decaying kernel k epsilon, and to define an integral operator g epsilon, define like scale with this epsilon and minus d over 2. So this integral over the manifold, so volume integral over a sub-Riemannian manifold on Rn, stay away from the boundary. So let's say the manifold has close or maybe has boundary, then stay away from the boundary. If you assume that your function is C3 differentiable, then you can derive this asymptotic expansion. So first order, you're going to get the function alone, scaled by some constant, and then in the order epsilon term, you get this Laplace-Beltrami operator. And then there's a high epsilon.
Do you need to wait a bit?
Sorry.
Which epsilon? Can you write down an example of this? Then let's show.
So okay.
D is the dimension.
Yes, D is the dimension of my
G is the dimension.
Yes, so D dimensions and
Yeah, that's fine.
and D usually you hope to be let's say.
Omega is the volume form on
Sorry?
Omega is the volume form on something else.
Omega.
Omega is the volume form of something else.
It's just some quantity, some functions that usually we don't care about. We want to get rid of using the asymptotic expansion. Okay. But let's say if there are statistics in the audience, let's just say, I don't know, right? If you ignore the order epsilon terms, right, and then you discretize your integral with Monte Carlo, that's exactly kernel density estimation, where F is the density, right? You average the kernel over the data you draw from a certain density F, and you get the density. So essentially, this is like sort of like a higher order asymptotic expansion sitting around. There is this, under the assumption the data lie on a smooth Riemannian manifold, you get that. Okay. So then diffusion maps basically capitalize this asymptotic expansion by doing the following algebraic expansion. Just doing some algebraic manipulations. So you move around, you can actually show that this L epsilon, which is 1 over epsilon p, this is just some normalized integral operator, if you wish. Okay, it's giving you a Laplace-Beltrami up to epsilon. Okay, basically, is that clear so far? Okay, So this is just the simplest version I'm showing here just for the presentation. If you read the paper, if your data lie on non-uniform density, there's a way, like to get remove the bias induced by the density. Okay. Now, like I say, diffusion maps basically is a discretizations that capitalizing this algebraic manipulation. So how do we do this? Okay. You start with this kernel, right? Okay. You give a data set line Rn. So it's just a simpler version. So one version. Okay. So what you do is the following. You take, here's average the kernel over the training data. Compute this. You normalize your kernel. You normalize your Gaussian kernel once. And then you take this normalized kernel, you average it one more time, and then you divide by that normalization. You construct P epsilon n as a Markov matrix, Markov kernel. Okay, so basically, here's a discretization. The reason why we do discretizations is because we don't know the measure. We don't know the entire manifold usually. All you have is just data that you assume lie on them. Okay. Now, just to give you something to hang on, right? Suppose I compute eigenvectors of this matrix, okay, on something that you know very well. Suppose my data lie uniformly distributed on the circle. Okay, so we know from our PDE 101 in the undergraduate that if you take Laplacian on the unit circle, then we know the eigenfunctions, which is Fourier series e to the ikx, right? So if you do this algorithm, you construct them, right? The appropriate scale, see that you get sine x, cosine x, sine 2x, cosine 2x, and so on and so forth. Okay, so you approximate this using this matrix, and then you take the eigenvectors, you normalize it appropriately. That's what you get. On the bottom, it's like another Sturm-Liouville problem. Say your data lie from your data lie on the real line. Okay, you draw it distributed Gaussian. The Sturm-Liouville problem, right, will give you the eigenfunction as Hermite polynomials. So there you go. You got the leading eigenvectors in Hermite polynomials. So basically, looking at this, something that you probably want to hang on in your head is like diffusion maps literally give you a way to approximate generalized eigenbasis on a domain defined by just the data points, right? So if the data points lie on some crazy manifold, then you're probably gonna get the basis representation on this manifold.
Did you do something careful on the second example? Yeah.
On this particular one example, I forget actually. We do probably a variable bandwidth version. So I have the variable bandwidth diffusion mass paper with Tars Berry. Probably we do that. It's just some normalizations, some sort of different normalization that
Different to what you showed.
yeah, different, right? But there's since you asked, later I'll talk about the boundary differently. Okay, this one has no boundary. This is just R, right?
For the first one. What?
This is Hermite, right? This is R.
I see.
But then the measure, the density of the data is Gaussian. So this is no boundary.
Okay, sorry. I was
So the
thinking-
boundary is totally different. Like let me, I'll hang on and I'll tell you the story about that since you asked. Okay, it's irrelevant to this talk, but okay. So now let me walk through the literature. Okay, basically for smooth manifold. Okay, it is well known that if you compute this, this matrix minus identity divided by epsilon, it converges to a Laplacian in various sense. So here I'm just trying to write it down in a very simplistic, meaning as epsilon goes to 0 after n. In reality, when we write the theorem, there's a combinations of epsilon has to be larger than a certain scale of n and so on, so that when you take the n goes to infinity, this is all sweet going to the Laplacian. Okay. So pointwise convergence on closed manifold. Closed manifolds mean compact with no boundary. This was first results quite Lafon and Singer with rates. Okay. Spectral convergence. Okay, on flat torus, I think Wormel, Caroline has. results on this. On the general closed manifold, Calder and Trilos probably has the best rates. For Dirichlet boundary, so solving Sturm-Liouville with Dirichlet boundary. So I have a convergence on this. So this one, the algorithm is just slightly different than what I showed you earlier. How different is basically you do the standard diffusion maps you want, right? And then you look at the matrix, and then you just take sub matrix and then throw away those connectivity for sufficiently close to the boundary. So I didn't invent that algorithm. I was sitting around in University of Chicago. Somebody told me do that. And then my question was like, at the time, this is before COVID, I was like, how far we need to truncate? When you truncate, you really get, I show it numerically. So that paper that we published tell you how far you need to truncate in terms of epsilon and n. Okay. Now, eigenvectors on L infinity, but in L infinity norm on training data. Okay, so basically eigenvectors really. They have several results here. Johnson and Wu. This is one of the results that I actually will use. Calder and Trilos also has one result. So they have convergence on all of this. Okay. So now, what is diffusion maps kernel? So those are diffusion maps algorithms. So now what is diffusion maps kernel? This is central object that I will use for learning dynamical systems. Okay. So let's consider the same Gaussian RBF kernel as before. Okay, just the same Gaussian kernel, but let's do the normalization just slightly different. Okay, so I add 1/n factor on here. The first normalization is still the same, nothing changed. I average again, but the second normalization, I take this symmetric normalizations rather than make it a Markov kernel. So the reason I want symmetrize is then because I can talk about I can talk about the RKHS space and so on and so forth because now it's a kernel. I at least at this point of my life, I only understood symmetric kernel. Non-symmetric kernel, I don't know. Okay. Yes.
So in the Koldman-Lafont,
Yes.
there's this alpha. That would be your first normalization. Alpha equals 1.
Yes.
And then you do essentially normalization alpha equals a half.
No, this is not alpha equal. This is not alpha. This is 1, and then the second normalization, rather than taking divided by q
So
in
row
x.
normalization, yes.
So I take q1/2 here and q1/2 the other one.
Okay. So instead of row normalization, you do a symmetric normalization.
Yeah, I do symmetric normalization. The reason,
Mhm.
okay, I'll tell you the reason is basically, okay, number 2. This is the reason. Eigenvalues of the P obtained by the diffusion maps, right, are exactly the eigenvalues of 1/n of this.
Okay.
Okay,
And then you
so
are symmetric.
yeah, because they are diagonally, equivalent. Okay, that's the reason. The factor 1/n, I'm just adding so that it eases the analysis. I want to interpret like this Q, right, is essentially, sort of a Monte Carlo approximation to that. So it's an integral operator over point, like empirical measure.
But Beckman has some bistochastic version.
He does have bistochastic version. No, I didn't do any of that.
I think it's also maybe, I'm not sure if it's symmetric or not, maybe just bistochastic.
You can do a bistochastic normalization that's symmetric with synchron.
Yeah, but I'm not doing any synchron, nothing.
Okay, but
This is just,
so, okay, I guess my question is it related? I mean, here, is it it's just purely symmetric, not necessarily stochastic?
it's just symmetric. No, it's not, in the sum, and I didn't normalize the sum to be 1 and so on. It's not a Markov kernel. Okay.
So what's the purpose of the second normalization?
I want to make it symmetric, right?
So symmetric. to the
Right.
first one,
Right. So,
or even the K itself is symmetric.
well, yeah, this is symmetric, but it doesn't converge to anything that I want. But with this, it does converge to something that I want. Okay. All right. Maybe the next slide will clarify. Heat current estimation. All right. So there is this result okay, by Dunson and Wu, is saying the following. For d-dimensional manifold, literally, if you take this, okay, the symmetrized version, okay, to the power of p over epsilon, for appropriate t larger than certain number that basically decay as a function of n, okay, it converges to this following expression, which is the heat kernel corresponding to the Laplace-Beltrami operator. So with appropriate rate, I don't want to make a big fuss about it. So lambda and phi here, this is just representing eigensolution of the Laplace-Beltrami operator. Okay, so they have these results in high probability, but the convergence here is L infinity over the training data over X. Okay, so X is just finite over training data. So recently, I just finished this paper like about a week or 2 weeks ago. We show the same convergence rate, but over L infinity over the manifold. So here, basically, just to give you a feel of what's going on is that we also account for nice strong interpolations of this guy for all of these other points that are not on the training data. Okay, so convergence rate is the same, but the choice of epsilon decays, it has to be slower. This is due to the fact that we need to interpolate. Okay, so there's all details in this paper. So basically, we get the same convergence to the heat kernel. Okay. Now, what is the implication? Why do I want this convergence in the entire manifold? If the kernel converges like continuously, right, or in L infinity like this, then I can say, oh, the RKHS, the reproducing kernel Hilbert space induced by my diffusion maps kernel in the limit converge to the RKHS induced by the heat kernel. So I can understand, oh, maybe this is the natural object, this is the natural library I should have constructed from the data. So that's what the whole game. Okay. So going back to the story of the beginning of the talk, I said like, how do you capitalize the fact that high dimensional data set, low dimensional manifold, perhaps find a better basis. So the better basis is like this dictionary, which is this dictionary that you're trying to get. So if you represent function using this dictionary, probably are more efficient to learn. Okay, so that's the whole thing. All right. So those are, some sort of like representing functions. By the way, in this paper, we also prove some wrist bound, like you were talking about the wrist bound earlier, right? So we also prove wrist bound for if you apply kernel ridge regression on using this kernel, okay, on some interpolation space. So we also prove that. We also identify what type of function this kernel like to represent, because ultimately, if you pick a particular kernel, you cannot kill everything, right? There are type of function where this kernel is good to regress to represent. There are type of function that it doesn't. Okay. So now let's go to learning dynamical systems. Okay, from time series. So let me talk about what I want to do with this, what I have in my mind. So here's the learning task. Say I want to estimate. This is just a solution operator of the dynamical systems. Okay, so it takes Rn base space, send it into some sort of invariant sets, subset of Rn. Let's satisfy this. I think either you model it this way, or you can model like the residual is solving that. Okay, so one or the other. Okay, let's just concentrate on this one. So why we consider both, you might ask, is because sometimes, let's just say if the dynamical system is ODE, for instance, right? Let's just say it's a solution of ODE. If the ODE is actually stiff, right, you learn it this way, we get a better result empirical. But if the ODE is non-stiff, usually you use explicit method to solve it, and then basically all you need is just to learn the residual because it's explicit at the right time. We found that numerically, if it's not stiff, you can use the right one, but if it's stiff, use the left one. For whatever purpose here, it doesn't matter. Okay. Now, in our application here, the data sets will be solutions of ODEs, PDEs, on a finite sets of basically spatial discrete points. The forward invariant measure in this particular application, it could be smooth, it could be, fractal sets, usually this is low dimension relative to Rn. So this is why I'm sort of like, oh, okay, if this thing is low dimensional relative to Rn, then let me find a tool to represent this. And that's one tool that I showed you was the first part of the talk. That's all. Yes.
So you take transients into account because you start in Rn and then converge to the manifold, or is it?
Usually we don't take transient into this.
So it's from M to M essentially.
Essentially, yeah.
Okay.
Essentially, I don't think, I don't remember whether we try or not. It does numerics, and I don't do numerics. I mean, the student does that, so I don't remember. I don't think so. Right. Okay. So practical consideration here is like, usually you have short training data time series. Okay. So you want a scalable training procedure to do this, stable and sort of things. Okay. And then we'll also touch upon when the training data are corrupted by noise. Okay. So, okay, all right. So those are the goal. And what I'm going to do is I'm going to apply kernel-rich regression as my model rather than using neural network. So what is a kernel-rich regression? This is written for this particular application. It's like, this is one component of the map, the solution operator map. Okay, I'm gonna approximate this basically using this model, a kernel multiplied by some parameters. Okay, this is just the I component. So if you have n-dimensional phase space, this is one at a time. Okay, with appropriate scalar value kernel. So the kernel can be the diffusion math kernel, or it can be other type of kernel if you want. Okay. So basically, if I given a pair of data, xm and ym, so in my case, because I'm trying to learn the solution operator, so my labels is the solution at the next time. So in this case, right? So we can identify this guy by basically just solving a linear regression problem. Okay, so this is just your least square. I regularize using standard RKHS norm on this space of functions. So that's just giving you this. And your solution is, you can write it explicitly. This is this. You solve n by n linear problem where this capital N is the size of your training data. Okay? So it's simple. Okay? I want to stress out that every time you solve this, right? Every time you solve this, the solutions here depends on two parameters. Epsilon is the bandwidth of the kernel that you have to tune. And lambda is just the regularization parameter. So these two parameters is key to make this work. So if you tune that badly, when you apply it to generalization or test data, you're screwed. Okay? So how do you tune epsilon and delta? Right? So we look upon the literature. Of course, there's a couple of things. Under assumption of gazillion assumptions, you can use mathematical assumption to balance. Those are not going to give you any good result because most of the time you bound all the hidden constant going to kill you. So you can't do that. In practice, what people do is use validations. So you have training data, you have validation data. So how do you do validation? For instance, you pick epsilon and delta, right? You pick one epsilon and delta, you solve this alpha, you have your model, and then you test it against the validation data, right? Now, the question is like, how do we test on validation? Which metric do I use to validate? If I use exactly this metric, this particular loss function to validate, basically all I'm saying is like in validation, I only see one iterate of my model, right? Remember, this is my model. This is just like one iteration of my model. Okay? Then in practice, if you do that, right, your prediction, one iterate, will be really good. The second iterate, the third iterate is going to blow off. Like the prediction is going to be really bad. Okay, this is probably also the underlying reason. Like a lot of these neural networks modeling. Right, we try with so many of this. Let's say let me not say LSTM, but people are like to use neural ODE, right? In the neural ODE, exactly, you want to learn the factor field, right? And then you try to fit the data integral over time, right? But in practice, you cannot actually fit it to a very long time, right? The reason is vanishing gradient and all that kind of things, right? So that's why they don't actually work very well for chaotic dynamical systems. What they always show in their paper is like they show it on a very simple, dynamics, which is kind of sad, in my opinion. Okay, so that what I'm alluding here is like to choose this epsilon delta, right? It matters to design a good validation or a good validation metric. Okay, so what is a good validation metric? What is the purpose here, right, for the solution operator? I want to be able to predict my dynamical system for a long time. Am I right? When I iterate it, I'm good. So let's design a validation metric. Okay. So let's say, suppose v tilde here, okay, for a choice of epsilon delta, this is a notation for my estimate after I do my KR. Okay. So let's consider the following validation metric. So if the system is not chaotic, right, you basically, iterate this and compare to your validation over a horizon of time. Like this, I denote it by NV, the length of the validation data. You just do that, right? And then you pick, epsilon and delta that give you the smallest thing, the smallest error. That's one way. Because why this is natural? Because at the end of the day, when you're doing the practice, this is what you want to measure. It's like, how good is my prediction over very long, right? Or for chaotic system, this is another metric called valid prediction time. Basically, it's kind of telling you, if I look at average normalized error, so this is just standard deviations on each directions, average normalized error on the validation, less than whatever precision you wish, okay? And then you just normalize them by Lyapunov time. So then this is sort of a valid prediction time. This is another metric. So you want this, the longest VPT. The longest VPT you get in validation will hopefully give you the longest VPT in the test set. Okay? Usually we just test this using several trajectories. So let me show you, sort of, yes.
Can I ask, so the K that you're using for the prediction, is that the K hat or whatever you had at the beginning, or is it unrelated?
It's related. We will use that K hat with the diffusion maps kernel, and then maybe you can ask, do you need to use that? Right?
So on the previous slides, when you were describing your model,
Yes.
in practice, that's a K hat.
You mean the
Like this, top,
top,
the first display equation.
this one?
Yeah, is that?
I'm going to use the did I use K hat here? I'm going to use this one,
Okay, which is the final thing.
the final kernel. But then you can ask me, what if you just use K tilde, right? What's the use of this kernel, right? That's a valid question, right? Because ultimately, K epsilon n is just a scaled Gaussian, right? So then the question is like, how good is this compared to Gaussian, right?
Or even K hat.
K hat, I never tried. I never even tried because
At least it
you can.
compensates for the density, right?
Yeah, you can numerically. It's just that theoretically or whatever, it doesn't cross around my head. What is this thing's gonna estimate? At least with the final kernel, it has this heat kernel stuff. It kind of ground me in that. Okay. Although for dynamical systems and for manifold and so on, it's very hard to say. This is some open problem for the audience. Yes.
For the validation equation.
Yes.
Yeah.
So for the non-chaotic system, if I understand correctly, so in your validation set, you have like say a trajectory of length 3.
Yes.
So what is comparing is the true value at time 1 with the one step ahead prediction at time 1. The true value at time 2 with the one step prediction at time 2.
Oh, sorry. Iterate.
Oh, so you're using the predicted value at time 1 to predict the predicted value.
Yeah. Iterate.
Machine learning people normally do that?
I don't know which machine learning people you're doing. I don't know.
People who work on time series?
I have no idea.
Oh,
I have no idea. Okay. So, okay, so. All right. Is that good? Yes.
Yeah, first, I think it is what time series people do. I'm curious. This is now, for what is the gamma here?
Yeah.
Oh, it's just
It's the hyperparameter.
it's a hyperparameter. Let's just say the following. Okay, in my predictions, I want to find the longest time I can predict up to resolution 10 to the minus 8.
Yeah.
This is 10 to the minus 8.
So this is not like a non-smooth objective.
It's just a standard metric. It's just a metric, right? Right. I mean, people use this. I didn't invent this. Like Georg Gottwald came up with this. I saw that paper. We're like, oh, he said I can predict 13 Lyapunov exponent, Lyapunov time length. So I'm going to show you something.
So what was the time did that? I mean, why do you stop at -1? I mean, usually like people when they do time series prediction, they also get further in the past to be able to further predict in the future, right?
People do that. Yeah, here I'm just because my reason is like, wait a second, I saw the entire state, right? And I know the dynamics is Markovian in principle. So just do this, right? If you see partial observations, then there's a compelling reason for you to, look at the map that depends also on the class.
Yeah, but usually you don't know.
Huh?
Usually you don't know whether what you have. I mean, just have a time series and then
Yeah, for this is like, basically, but this is at this point we're just gonna test on a lot of problem that
Yeah.
there will be a problem that I don't know actually.
Sorry, I'm sorry if I missed it. Little n areas.
Sorry?
What's your little n? Is this your
Oh, little n is the dimension of the phase space. So this is error in each direction.
Oh,
This is
relative.
relative.
It's not into the Lyapunov time.
No. This is a relative error in each direction.
Okay.
So, subtract the error divided by the standard deviation on that
Yeah.
direction. You average them,
Yeah,
and if you're happy up to this resolution, you see how big is the n,
yeah.
and then you normalize with the Lyapunov time.
Lyapunov time. Yes.
Yes.
I wasn't quite sure.
Okay.
Okay.
Good. So let me show you, a landscape of PPT as a function of epsilon and lambda. These are two parameters we want to find, right? So epsilon and lambda, right? In this box of landscape, you see how the PPT vary. So if you look at one of these box, right, you see, obviously I'm going to choose epsilon and lambda somewhere in here, right, where the PPT is very high. Right, so there's a smooth transition. So it actually matters how you choose this, because if you choose it somewhere here, you're screwed. Your prediction might not be that good, right? So basically, this is sort of validation. Is like in practice, at this point, we just do something very traditional, I would say. You pick you use an empirical method to get a reference. You start, and then you basically find a box, and then you randomly sample epsilon and delta, and then you validate. Something very traditional. Maybe yes.
So but how does this compare, I mean, to our work? Where we were looking at the estimate of Lyapunov exponents, and then saying that we are going to estimate this epsilon and lambda under the premise that the kernel is good if the estimate of the Lyapunov exponent from data doesn't change much.
Oh, so you use a metric. Your metric is to check the Lyapunov exponent.
Yeah. So
Then let me ask you.
Yeah. So you see that I mean, here you are using VPT, but so if you come back, I mean, we had like multiple metrics, including
Yes.
what you are saying that I want to go as far in the future, and then we were using Lyapunov.
How expensive is this compute the Lyapunov exponent for each time compared to my VPT?
Yeah, no, this is what I'm asking you because our paper was like 5 years ago. Right?
I don't know.
Yeah.
I don't know. But you use a metric. So what he's saying is like rather than using VPT metric, get your estimator, compare Lyapunov exponent. So my question will be like, it depends. If your computational cost to compute the Lyapunov exponent is sweet, I'll take that. I'm not saying PPT to be one metric.
Yeah, I don't know. Yeah.
I
I used my laptop to compute, but I don't remember. It was like what?
I use my graduate students to compute, so I don't. Okay.
Yeah, maybe my laptop had doctorate student. Yeah.
Okay. So this is how we determine epsilon and lambda, right, in validation. And then you do, then the question will be, probably, the question will be this. This is the right question. It's like, when you're doing this VPT comparison in either of this, right, how long of a validation data set can be? You have a training data set, you have a validation data set, right? I'm saying I'm comparing the prediction, right? So how long is that? That matters, right? So, okay. So here's a test PPT, the higher the better, using two different kernels. The diffusion maps kernel is the black, the green is the RBF kernel, as a function of your validation length. So in this case, right, I mean, I hate this. I just keep forgetting to ask my student to basically replace the x-axis to be the diagonal of time. But I'm just telling you, one diagonal of time is about 1.9. So this is about 5, right? So what this picture is actually saying the following. If I validate for about 5 seconds, right, and I test it, look, I can get pretty long PPT. The longer validations, at one point it will saturate. Right, so this is long, this is short.
You're optimizing separately, epsilon and
Yeah. This is like these statistics, like each of these point in this curve, right? The mean is taking over 500 models. Why 500 model? Each model has each different data set, each different training and validations. And on each model, we test it on 500 different initial conditions for prediction. So this is average over 500 squared. So it's quite robust here.
just means exponential.
Yeah, just this one, no normalization, nothing. Right. Of course, in this example, now it's very hard to analyze because we're talking about, hey, it's fractal, it's no manifold, and who knows what. Right? Okay, so here's sort of a typical example of how long in the test prediction you can predict. You know, even new initial conditions you can predict. On the bottom is the RBF, on the top is diffusion maps. So those who curious about PPT, so PPT is saying like, okay, up to whatever resolution, here's the length I can predict. So, but here, right, the difference is insignificant at this point. All I'm going to tell you is like, actually, with this picture, I'm telling you, even on this very simple example, you don't have to do all kind of neural network and things. Using kernel-rich regression in Gaussian kernel is even worse. Provided you tune the epsilon and lambda correctly. You don't need anything crazy to do this. This is a very simple example. Okay? Of course, you can do neural networks, you can do NODE. Oh, you're gonna try. They just go up to here, about 3 or 4. With neural ODE, we try like, you know, like with this group of people who from it Molly, he knows how to do that. So I was like, okay, clean it, right? On the KS, Kuramoto-Sipasinski, so this is another test example, right? The diffusion maps is giving you slightly better PPT compared to the KS, compared to the RBF kernel. So here's just showing spatial as a function of the diagonal of time. This is sort of the error of predictions. This is just showing you using 2 different kernels under the same method, okay? If you want to see quantitative, okay, you construct your gram matrix of your kernel on different size of data. The larger the data sets, you know, you see all of this better PPT. For the KS, you need a larger, higher dimensions. Okay, so you can actually reach higher if you construct your kernel really large. So these are sort of the level of time that you can expect, and these results are very robust. The top is 500 squared average. The bottom is 500 times 50 squared because I don't have the computational capacity to go around that. It takes a long time to basically train. Okay, so we can try now take KS Kuramoto-Sipasinski equations, right? You change the dissipation parameters so that it gives you a traveling solutions in this case. This is just the traveling solutions. Okay, you can see it's the traveling wave. Sorry. So the diffusion map kernel regression is top. See, 10 to the minus 5 error. Sorry, one more time, it's too fast. The RBF kernel also works. See the error? This is neural ODE. After a long time, become garbage. The right-hand side here, this is using latent dynamics networks. This is something created by a numerical analyst, Quaternoni.
Yeah.
Basically, autoencoder is in the architecture. Okay, so those are
neural ODE we're using. Could be anything on this.
sorry.
When you say neural ODE, I mean there's billions of neural ODEs. What sort of what were you using?
I have no idea. It's my student. I ask my students. Okay. Okay, it's just neural ODE.
No, there's no just neural. There's hundreds of.
Okay, so there are details in the papers. I don't know. So I want to tell you, it's like for this problem, right? The traveling dynamics. If you actually apply a dimensional reduction method, so here, for instance, we apply isomaps, you'll see in the latent coordinates, they're just very simple dynamics. This is sort of like in latent coordinates. You can see the dynamics lie on low dimensional low dimensional sets, if you wish, right? But I don't use any of this in our method. Okay, I just show you, the picture, what it looks like. Because if I try to use any of that in the method, let's say I try to use isomaps, then I am killing myself on the algorithmic complexity. Because to do isomaps or to do diffusion maps properly, you have to do eigenvalue decompositions. I don't want to be subject to that error. So we just use the kernel directly. Okay. Now, here's another example, closer to aerospace dynamics. So it's like, here's a, basically, it's like a vertical strength. This is what I plot here is a vertical strength of a fluid, basically under this sort of a plunging and pitching behavior. So on a certain angle and so on. This is, it looks complicated in the phase space, like a 10 to the 5, but then when you do isomap on it, look, it's just one-dimensional manifold, literally. The dynamics is just so simple. So we're saying like, we should be able to kill this very easily, right? So here's what we try, okay? You look train, and then you test it on different phase, different angle, okay? So those are the truth on the top, right? The diffusion maps predictions, this is sort of the error, the blue, okay? The RBF prediction, it's going banana. They're not happy. So this kernel is not good for this problem, apparently. We compare with this method that we believe is designed to solve this problem. This is the SDMP by Albert Matthew. Here, right? So that's the green, right? So it's we're there. We're kind of there. Okay. So, all right. So those are story of clean data set. It doesn't mean anything. Now let's show you. Okay. Now noisy data set. Okay. All right. So noisy data set. So I need another tools. So I need some sort of filterings. So look and search upon literature. So there's this work by Messenger and boards. Basically, what they do is like they introduce a sort of loss functions that is not in the L2 loss, but in the weak form loss. So the idea is just as following. I like this paper, but there are some part that I like about this paper, but there are all of the part that I don't like about the paper. I'll just tell you in private what I don't like. So consider you're learning this factor field. Okay, you want to learn F, solution of the dynamical systems, where now the data is basically the solution plus noise. This is what they consider. Okay, if you do standard loss, basically, right, you take x prime minus f, right? You take whatever norm, discretize this guys, this error loss using the data, right? Then you can immediately see a problem. You say like, wait a second, my data that are available is just noisy. How am I going to estimate x prime? Right? Your f, you're going to replace it with function that you like, neural ODE, or you can do kernel or anything you like. Okay? Right. So then what they say is like, here's how to get around that. Rather than doing weak form standard loss like this, let's impose this. Take the test functions on a compact support domain, okay, let's say omega j, and then you impose your ODE in weak sense. So you take your ODE, you know, multiply by test functions, set it equal to 0. Why do you do this? If you look at the first term now, x prime times phi, right? If I do integration by parts on the first part, I can switch. Okay, so now you look at, here's an expression. This is what I want this to be 0. Now, if you look at this expression carefully, if I only have the data, it's noisy data, I just plug this in. You see, I just plug this in. I don't need to estimate derivative. This is their whole idea. So I thought, oh, this is interesting, right? But they have a set of works. They have, maybe they published tons of work after this. You know, this is just the 2 that I saw. They never actually explain there is a filtering mechanism behind this. Okay, so basically this is what they do. Once they have this is switch integration by parts. They pick a basis. Okay, the basis of choice is just the weight for the Jacobi polynomials. Okay, on a certain bandwidth, and then, you know, basically Pj is just a dilation of that functions. So then the weak form loss is this. So this is what they minimize. Okay, you see now. Okay, this is nice, but there are a couple of things going on here, right? There are several parameters. P is the order of polynomial you have to pick, right? Because this function, the p, the original p, is just looking like this. Most of the time, it's just looking something like this. I don't know, I'm not good at picture. This is sort of compact support L. So usually looking like that, you know. So then you have to choose the P, the sharpness, how it turns, the length of the compact support, and then these dilations here by H. Say, oh, I'm going to integrate it over this domain, and then maybe I'm going to integrate it over maybe another one, maybe here. Then the distance between here and that H, right? It's just like this wavelet thing. In the wavelet, they call it like dilations, right? The length 0 to L, they call it the frequency in the wavelet parameter. So 2 parameters, but here you have P, and also you have how many of this, how many representation, right? But whatever this is, to me, when I look at this, I'm like, wait a second, this is just, you are representing a signal using finite number of bases. This is how I thought about it. So, okay. So, thinking about that, so I'm making a connection with the classical low-pass filter. So I'm thinking, I want to explain these things, you know, using low-pass filter before I use it for something else. So imagine you have a function u, okay, which is a clean u plus some noise. So in this case, for simplicity, later the noise we just assume is variance, but it have a variance eta, it's Gaussian. You don't have to if you don't want to do analysis. Then you define the following, right? You take the signal projected on this basis, or, you know, taking the product with this phi, right? This is integrating this. Of course, in practice, we don't know the signal completely. All we know is like just the signal we solve at whatever time. So you have to do some numerical quadrature to approximate this. So, okay, in linear algebra, you can write it, okay, C is this. You see, phi is just a representation of the basis. W is just a diagonal matrix of the weight. U is your noisy signal, okay? So I'm just gonna ignore all the dimension here just for it. Now, let me express the filter signal. So let's say I have a filter signal represented by linear superpositions of these bases. This basis is band limited functions, right? So in linear algebra, you know, you write it down, this is just that, okay? And then straightforward calculation, you can write this way. U hat is P of U, okay, where the P will just be this, okay? This is effectively is a orthogonal projection under a weighted inner product. So that guy u hat equal to p of u is somehow a discrete approximation of u hat equal to some integral of some filter of your noisy data. Low pass filter. You look at low pass filter literature, that's exactly what it is. And here we're just characterizing the filter is like this. Okay, so that's sort of, to me, is sort of explaining, oh, this is why it works. We look at actually when we reconstruct using a particular choice of P, K, and so on, right? You see the noisy observations, ground truth is that we just tested it in reconstruction. Oh, you're really filtering the data. Okay. Once we have this filtering, understand that this is just a filtering algorithm. Of course, you can, go back to the literature and see how they do analysis on the error. So there's a bias, variance, decompositions. For that particular band limited function, we do the analysis. The variance is increasing as a function of k star, the number of bases you use. Okay. Like in the previous talk, there was a picture like the U shape, right? So in that case, it's like the more data you use, then the variance in this case is not shaping like this, but it's linear. Okay. The bias, this is very hard to get. Well, I can get an analytic expression, but I think the analytical expression that we get is rather useless to tell you how to determine this parameter, H, L, and P. Yes.
What is the band limited signal?
This is the band limited function that we use, like P. It's this.
Oh, so you assume, okay.
We pick the basis, and I pick this basis.
Okay.
I pick this basis, it looks like this. So it's band limited. Right? So basically, I'm saying this signal is represented by linear superpositions of the dilated.
So then when you choose K star, are you making an assumption that the underlying data has is band limited as well?
Underlying data is no, I don't have any assumption like that. It's just the number of size of K star will tell you the error. The more you do, you see, if you don't have a bias, right, then the error will be increasing as a function of K star. Remember, like in the previous talk, we got this picture, very nice picture, like whatever complexity. So let's just say K star. The complexity here is the error. Call it risk. In the previous picture, it's like this, right? This is usually comes from here's a bias, here's the variance in statistics. My variance is not that, but it's linear. Analytically, we can compute it. Basically, that. Okay. All right. So now, having this understanding that imposing weak form is essentially doing low pass filter. So we do the following modification in our method. Okay. Initially, I want to solve this problem y equal kernel, right? Y is my dynamical system. I model with the kernel. So let's project them, right? Let's project to this. So here's the linear algebra notation. Project, multiply on the left by the basis and weight it. This is the quadrature. When you project this, if I define my alpha to be such things, then basically you have sort of like a projected kernels. So instead of it's in capital N by capital N, now it's K star and K star. So projected the kernels. The KRR solutions, now you're fitting the projected kernels. This is the projected data and everything. It's the same KRR, but in a projected space. Okay, so that's all it is. You take your old method, you project using this. Okay, you determine your epsilon delta the same way how you determine on the other case. Okay, now then here come the questions. Okay, the question is the following, right? Suppose you know how to filter the data. I show you how you filter the data. So then one natural question is, why just not use your standard KRR on the filter data? You can do that, right? Right? You can use the strong formulation L2, but apply it on the filter data. You can do that, right? The second is like in the formulation above, right? this y, right, or essentially this is approximating an integral. We're integrating over noisy data. Why can't I replace this y with the filter data too? I can't. Or replacing k, the gram matrix evaluated at the filter data. I can't do that. Okay. Right. So there are many options in this case, right? So let's test that. So that's what I said earlier. Now, if you look at this picture, the PPT is lower. Okay, then I say whatever result that give you PPT 13 on the clean data is meaningless, because now this is the real problem. You have a little bit of noise, 5% of noise. On the left, this is KS. On the right, this is sorry, on the left is L63 and this is KS. Let's just focus on one. So what happened here? If you don't filter the noise, you just apply the KRR with a strong sense, normal, the old one. That's the PPT you're going to get. Your prediction skill is very low, very short. Okay, these guys, Rafda, okay, if you know Georg Gottwald, you know he does that. So what he does is actually he uses a random, I think name come from random features models, and DA means data assimilation. So how he deal with the noise is he apply Kalman filter to estimate the parameters in the random feature model. That's what he does. So if you do Rafda on this, right, you get about there. Okay. So here we use strong formulation, but we filter the data using simlets, like a type of wavelet. We got around there, use this particular polynomial filter. You get a little better, but here's the weak form with Gaussian, weak form with diffusion maps. Okay, on unfiltered data and filtered data, you can get, you know, better and better. Okay, so those are sort of comparisons. But these are all toy examples. Let's do a real thing, right? Let's try it on the real thing. So my collaborator in aerospace, they know a lot of people who post a community challenge problem. So you can Google this website here. So they have many challenge problems. One of the challenge problem is predicting this fluid flow on a cavity. So basically, there's all details in the paper. Here's just a snapshots, for instance, of the horizontal velocity and vertical velocity. So there's an inlet on the boundary that is, we don't even know what it is. All it is like they give you snapshot of data sets. They say, okay, here's a training data. Give you about this size, 12,800 snapshots. And then the goal is the following, the challenge is the following. They give you, here's what you want to test, 32 seconds of this. So one of this is like this. They give you the first 70 snapshots, and they say you need to predict the 71 and so on. So this data set, we don't have it now. They haven't posted. Okay, so the challenge will end at the end of this year. Okay, so I think we're gonna try to improve it, and this is our first test. Okay, so since we don't have this data at hand, so this is what we do at this point. I take the same data set to do the training. I take the first 39 out of the 70 to do validation. Remember, I need training, validation, testing, right? And then I leave the rest 30 to do testing. Okay. So when I test, when I do testing, I take the data from this time 40 as initial condition. So I don't use any of this to test. Okay. So because at this point I don't know how is we don't have this data. Right? This is all we have at the point. Okay. Our employee, we just use this weak KRR. So here's sort of a little bit of quantitative result. This is a very high dimensional problem, by the way. Spatial resolution is about, this two dimensions, like two components. So total of about 15,000-ish. So it's really high. You want to put it in the kernel, you're gonna die. So what we did is the following. We say, okay, the through data on the U is on the first row, and this is the through data on the V. Okay. So what we're gonna do is like we follow some of the suggestion in the challenge is like do some truncation of P of P. So they provide codes for doing LSTM. So basically, you take you apply the principal component analysis, you reconstruct using, in this case, just 100 modes. So this is sort of the reconstructions of the truth. Okay, so the second row of this. So you can say this reconstruction of the truth is the object that we are going to train on. Okay, so that means it's like whatever you predict, at best, you can predict this, because that's the data set we have. Okay, we don't have a capacity to put in the entire thing. Okay, so if you use a weak kernel regression, this is what you get. This is prediction of time 1, time 2, time 5, and so on. Okay, so you should compare this with that. Right? You see, like all this dipole, you don't have it here if you use Gaussian kernel. This is if you use the diffusion match kernel. At least we have some eyeball norm. Okay, I don't know how to use LSTM. It's oversimplifying. Right, the bottom is use LSTM based on their codes. Okay, so there are some metrics. So we were trying this. Okay, so there are some comparison metric if you use LSTM. This is sort of the error. We use the diffusion maps kernel. This is what we get. Okay, so it begs for improvement. I'm not saying this is a method, but at least this method, we understand. It's just a kernel. It's just a linear prediction method, right? So, and the main point is like, perhaps if you understand or you can represent the low dimensional manifold where the data lie on close to, then maybe you pick that as the right features. So that's the whole message. So current progress. So I have extended this on a closure modeling. So we just haven't finished the manuscript. We extend to non-autonomous system, and then we're trying to understand we're trying to do Koopman spectral analysis. So basically, this is a pretty good prediction tools, but we try to look at do spectral analysis, see can we get the continuous spectrum on certain type of problem? Can we get the like a la Matthew Colebrook paper? We try to basically use their tools to extract what is this guy doing, in terms of spectral analysis. Can we interpret this model as what the dynamicists would like to interpret the model? Now, open problems is that at this point, I need a mathematical understanding of cross-validation strategy because we're using two different metrics. Okay, the old school computer science textbook, we understand if you're cross-validation using the same metric for learning functions, understand that. But this is now you suddenly have comparing temporal data. Now the complication is like now it's non-IID. Okay, the data is correlated, different metric and so on. Second is like, to me, it's just unclear why this works beyond manifold assumption. It's still unclear, it's complicated to say, right? Mathematically, this is sort of something that will probably keep me awake for a while. So reference, just 3 papers, okay.
Just for your question, but like mathematical understanding of cross-validation study, we may want to also look at another paper
Yeah.
ours where we looked at the reformulating cross-validation as form of complexity, where we don't actually need assumptions on the problem distribution here. I mean, I'll tell you everything.
Okay.
Yeah.
Okay.
Yeah.
Okay.
So very
Right, to quickly go. So when you're doing you estimate your function as a linear combination of the kernels. So there you're inputting your interpolating, right? One argument is
Yes.
So when you have the square root normalization,
Yes.
you're actually evaluating your q or whatever it was out of the square root
Yes.
at that general
Yes.
x point.
Yes.
Okay,
Yes.
okay.
Yes. Yes.
And
So Nystrom is done on both.
okay.
Yeah.
And I don't know if it's quick to go to the first or second slide where you have all the hats and tildes.
Yes. Hat tilde.
So was it the case that you're doing essentially the same operation twice, or is the second one different from the first?
I think it's I think it's different. In the Kaufman-Lafon argument, this is the first normalizations that make you bias from the sampling data set. And
The first one corrects for data.
yes,
Yes.
yes. The second one, this guy, I do the analysis. This is actually going to estimate 1 over density.
But mathematically, it's the same.
No,
You
no,
don't have square roots in the top. So you have square root in the top one.
no. I don't have square root in the top.
Top right. Oh,
I don't have square root. If I have a square root in the top, I'm estimating the gradient flow with grad log density Q. I don't do that.
And you cannot merge this into one thing. Like you really need these two
Yeah,
sequence of two.
two step.
You cannot make it one.
No, if you get one thing, you're not getting Laplace-Beltrami.
We're not getting Laplace Beltrami now.
I am. Oh, with this, I am. I'm getting Laplace-Beltrami. Spectrum and eigenfunctions.
Spectrum, yeah, just a different symmetric
Oh, yes,
normalization.
there are many normalizations.
Yeah, so
So try.
instead of rho, he does it symmetrically with the eigenvalues.
So the first one, I don't really understand what it's getting. I mean, if you want, on separately, I'll show you the asymptotic expansion.
It's nicer for like when you had your alphas, right? So if you didn't do anything, then you have lots of, if you, your data dense, you have lots of Gaussians nearby, you'd have to have low alphas to compensate for the fact you've got all these dense nearby. But after the first normalization, you reduce
Yeah.
the iterable Gaussians.
Yes.
So now your alphas can be more similar. And that's good for your ridge regression also. Your ridge regression is not biased.
Maybe we should try. Just so you're suggesting using this. We should try. I never tried. Yeah.
April?
Yeah, thank you. I think I don't fully understand. So from my understanding, the theorem that you have says like when I sample my data, it might be in like a very high dimensional space, but ultimately the data comes from like a manifold, so I'm getting some kind of like approximation of the Laplace-Beltrami eigenfunctions on this manifold. So it's effectively doing like it's choosing a nice set of functions that should represent the inherent manifold of the dynamics in some way, right? But then when you do the examples in the end, it seems like you're not really like using that to sort of do the dimension reduction because you're already just doing POD.
Oh,
that
after the
dimension
POD, okay,
reduces.
the POD was just for a technical reason. It's just for computational issues. It's just for computational issues. But then we apply the diffusion as kernel to regress on the POD component.
Right, but the
Right.
POD is already doing the
Right.
reducing onto a latent manifold for you.
Yes. Yes.
So what does the kernel ridge part?
The kernel ridge is just to give you the model for prediction.
Right, but I compare that to doing POD and then doing something very basic like SIMD.
Oh, you can try. You can try SIMD. I bet you're gonna try. You can try SIMD.
Well, the examples you showed are examples where I think Nathan has done a lot of stuff to show that like it works pretty well. Like Lorentz, KS, the airfoil.
Yeah, because you know the basis.
Yeah.
You know the basis. Here,
Okay.
here, I don't know anything, man. Like somebody just gave me this data.
Mhm.
This data is a pure data set.
Yeah.
Okay? It could be there are God knows gazillion of Python Laplacian that I don't even know. So if
Okay.
you don't put it in the library, you're screwed.
Now I see. Okay, now I see the level stuff. Yeah, thank you.
Any final question? If not, let's thank you.